Hi, everybody. These are your practice problems for symmetry, both reflectional and rotational symmetry. So the way this is going to go for these is I have a lot of different figures. Okay, so we're going to look at some examples for reflectional symmetry first, so drawing lines of symmetry in. Okay, and then we have some with rotational symmetry. That we're going to try out. So I'm going to do a couple, and then I'm going to have you pause the video and try some of these out on your own, and we'll see how you did. All right. So these are the easiest type of symmetry, I think, in my personal opinion, is the reflectional symmetry, drawing the lines of symmetry in there. Okay, so really you're just looking for all of the ways that you could take a shape and perfectly fold it in half. Okay, now if it helps you to actually like draw these shapes out like on a piece of paper, cut them out and actually physically fold them, then go ahead and do it, right? If that's something that's difficult for you to visualize, especially some of the lines of symmetry that show up on diagonals, if that's hard for you to visualize, then sometimes it does help to actually physically fold the shape, right? That definitely can help. All right, so I'm going to do these first three right here, and then I'm going to leave you to try the other six here, and we'll check back and see how you did. Okay, so in my lovely diamond square shape right here, there's lots of different ways I can fold this. I can obviously draw a line straight down the middle, a straight vertical line. That folds it exactly in half. I can also draw a straight horizontal line that folds it exactly in half, but I can also draw lines kind of on these diagonals right here, which mine don't often get right in the right spot. But know if you are doing this with me, if you're drawing a line and you're doing this with me in Cami, you can press shift when you're drawing lines, straight lines, either horizontal or vertical, and it will make the lines like perfectly straight. And you can also do it when you're doing it on a diagonal. It'll create an exact 45-degree angle here, which is, see if I go like this, and then I'm now going to press shift, right? And it moves a little bit less. So I can find one that's exactly 45 degrees here. And obviously that one was not very good. So let's try that one more time. Also didn't exactly divide in half, but I'll move it. Did the best I could there. Okay, so we have four lines of symmetry here. Okay. In number two, this is an equilateral triangle. You have all three sides that are congruent. Remember, the way we mark that is with little dash lines. Boom, 1, 2, 3, right? We mark them that way. That means congruent, right? Or congruent sides. Okay, so again, obviously I can draw a vertical line straight through the middle, right? I can't draw a horizontal line on this one because it won't make a perfect fold, but I can draw lines straight through each of my vertices here. Okay, and when I do, I have my three lines of symmetry here for this equilateral triangle. Okay, both the square and the equilateral triangle here are regular polygons. So if you remember in the previous video, one of the things I told you is that if you have regular polygons, the number of lines of symmetry is equal to both the order of rotational symmetry, so how many times you can turn the shape and it'll map back onto itself, and it's also equal to the number of sides, which you saw in both of these, right? Square has 4 sides, 4 lines of symmetry. Equilateral triangle has 3 sides, 3 lines of symmetry, but that only works for regular polygons, which I'm going to show you here in a second. Okay, with the rectangle. Okay, so if we're looking at the rectangle here, again, obviously I can fold it straight down the middle vertically, and I can fold it straight down the middle horizontally, right? So that's what your elementary school teachers would call like hamburger fold and hot dog fold, okay? But now, look, what a lot of people try to do with rectangles is they'll say, oh, there's another line right here. Okay, but that's not a perfect fold. What actually will happen if you fold it along this green line right here, it would fold and it would look, I'm trying to draw it with dashed lines here, okay? It would look something like this, okay? So not a perfect fold, right? It doesn't map or fold right back into itself, okay? All right. So it's true that this green line does create two congruent triangles, like two congruent right triangles, one kind of here in the top right, and one down here in the bottom left, but it's not a perfect fold, right? So only two lines of symmetry here. So 4 lines of symmetry here, 3 lines of symmetry here, 2 lines of symmetry here, okay? And this is what I meant by this rule where you have number of sides equals the lines of symmetry. It doesn't work when the sides are not the same length, when all the sides are not the same length, right? So like it didn't work for this rectangle here. All right, y'all. So I'm gonna pause the video here and do these other 6 right here. I would like you to do the same, draw the lines of symmetry, and let's see how you do with these. So check back with me in just a second to see if you got these correct. All right, folks, so here are your other 6 shapes. So that pentagon there has 5 lines of symmetry. That parallelogram that you see in the middle has only 2 lines of symmetry. The triangle that you see on the right-hand side is a scalene triangle. All 3 of its sides are different lengths, so it actually does not have any lines of symmetry. The triangle in the bottom left-hand corner is an isosceles triangle because you have 2 sides that are congruent, this one and this one. So you only have 1 line of symmetry there straight down the middle, right? And what you'll notice when you're drawing these lines of symmetry is the sides that are congruent will match up. If I folded this isosceles triangle over this pink line right here, this little congruence marker would land right on top of this little congruence marker, okay? For number 8, the 8th one you see here, this is an isosceles trapezoid. Same thing. I can't cut this off in the middle horizontally. I can't do any diagonal lines, but I can cut it vertically straight down the middle. And then number 9 is called a kite. That's actually the mathematical term for it. It looks like a kite that you fly in the sky. It's actually we call it a kite. Okay, and there's only 1 line of symmetry straight down the middle there. All right, so give me a second to fix my screen up, but that's all of the examples for reflectional symmetry. So let's look at some examples for rotational symmetry. All right, folks, so here we are. Let's try these. Okay, so I've got 6 different either names of shapes or actual shapes, and we want to figure out the order, and I know it says magnitude right here. I forgot to replace it. Really what I want here is the angle. Magnitude is just like the size of something. So like how much do we have to rotate it? So I'm looking for the angle of rotation here. Okay, so I'm going to do, let's see, I'm actually going to do number 1 and number 3 here. And then, well, no, I'll do 1 and 3 for you here. And then I'm going to have you try the others on your own. Okay, so we didn't get a picture for the first one. My golden rule in geometry is if they don't give you a picture, draw one. Sometimes it can help, right? If this is not something that you're used to doing. Okay, so remember with rotational symmetry, what you're doing is you want to put a dot in the middle of the picture and then a dot to track, right? And count how many times can I move that dot in one full 360-degree turn where the shape maps back onto itself, but the dot is in a different spot. Okay, so I can rotate this once for the dot to end up down here, twice for the dot to end up here, 3 times for the dot to end up here, and then a fourth time to get it back where it started. So my order here is 4, and that means my angle is 360 divided by 4, which is 90 degrees. Okay, so each of these turns, each of my little arrows here, is 90 degrees. Okay. All right, for number 3, it's very nice. We already have both a point in the middle as well as a drawing, so it's a little easier for us to track. Okay, so here, this is very similar to the one that I did in the example video for you, not the previous video, not the practice problems one, this one that we're watching right now. But this one, like if I took this and I rotated it 90 degrees only, it would look like that, right? So it wouldn't map back onto itself. So I actually have to rotate this all the way here for this dot to end up down here in the bottom right-hand corner to have this shape map back onto itself, and then go all the way back around. Okay, and now we're back where we started. So my order here is 2, and my angle is 360 divided by 2, which is 180 degrees. Okay, so I'm going to pause this and fill the rest of these in. I'd like for you to do the same, but there's one thing I want to tell you before you do that, which is this. A regular 40gon is a regular polygon with 40 sides. Okay, so kind of go back to that rule that I told you about earlier. And in the previous video as well, about the relationship between the number of sides of a regular polygon and the order of rotational symmetry, as well as the number of lines of reflectional symmetry, right? Don't try to draw this out because it would take you forever, okay? So I will see you all back here in just a moment to check your answers against mine. All right, folks, so here are the others filled in. Okay, so number 2 was a regular 40gon. That's actually what we call it. So remember, the rule for regular polygons is the number of sides is equal to the order of rotational symmetry. Okay, so the order here is 40, which means the angle is much smaller. It's only 9 degrees, which makes sense, right? If you're going to take a shape and rotate it 40 times in a 360 degree, like one full 360 degree turn, then that means each individual turn has to be much smaller, okay, and go less, not quite as far, right? Number 4 is has an order of 5 and an angle of 360 divided by 5, which is 72. Okay. Number 5 and 6 were a little bit tricky because you had to pay attention to some things. So in number 5, you had to pay attention to that some of these little endpoints are squares and others are circles. Okay, so if you only rotate, say, like from this circle to this circle, then the square will be in the wrong spot. Okay, so there's actually only 4. The order of this shape is actually only 4, even though it looks like it would be more. And then the angle is 90. And then similar thing for number 6. The outside shape could be rotated 6 times, like the hexagon, but if you only rotated it, say, from here, which this was my original dot that I was tracking, okay, if I went from here in the top right-hand corner over to here in the top left-hand corner, you get 2 shapes that are not the same because the triangle is rotating with it inside, right? So you have to pay attention to those things. So the order of this one is 3, and the angle is 360 divided by 3, which is 120, all right? And then there's one more thing down here that I want you guys to try, and then I'll show you the answer in a second. But here, I want you to see if you can take the alphabet and sort it into letters that have vertical symmetry, like the letter A, where you can divide, where you can draw a line of symmetry straight down the middle, a vertical line. So that would be a letter with vertical symmetry, but maybe without horizontal symmetry, right? Because if you took the letter A and cut it in half horizontally, right, that's not a perfect fold, okay? So like the letter A, for example, would have vertical symmetry but not horizontal symmetry. The letter B would be the opposite. It doesn't have vertical symmetry, but it does have horizontal symmetry. Okay, and then if you look at, say, the letter H, right? H has both. You can cut it in half horizontally and vertically. So H would go here in the middle. Okay, so I want you to see if you can sort the rest of the alphabet, okay, and then see if you can figure out if there are any letters with rotational symmetry as well. All right, so this is a little bit of a kind of like a little challenge problem. Let's see if we can sort these and then check back with me in a sec to see if you got this correct. All right, y'all. So here's the final sorting. So I found 7 letters with only vertical symmetry: A, M, T, U, V, W, and Y. I found 5 letters with only horizontal symmetry: B, C, D, E, and K. And then I found 4 that had both: H, I, O, and X. And then all of the others are my sad ones that don't have any. That are listed outside the Venn diagram, okay? And you can see I drew the lines of symmetry up here in the alphabet on the top. There are 7 letters here that have rotational symmetry, right? Where you can put a dot in the middle of each of those letters and have it rotate around itself, and it would still look like the same letter. Okay? So it's these 7, HINOSXZ. All right, y'all, so that is it for reflectional and rotational symmetry. So I'll see you in the next video on compositions of transformations. Bye, everybody.